Alright, we're finally ready to put all the little pieces together. We started off with having the this indeterminate frame, lateral load of 10 kip. We're trying to get the reactions, and we're going to ultimately get how much this thing sways up here at joints B and A. Our strategy was to remove the reaction at A, leaving us a primary structure that was now determinate. We put the real loads on there, let that then that tip deflect downwards because we no longer have that reaction there. Then we're going to come back and we're going to reapply it with a unit load at A, and then multiply the whole thing by the actual value of AY, add those two together, which meant that we had then to be compatible that is, compatible. To be compatible, we have then the displacement in the real system is equal to the sum of what happens in the two pieces. And in the real system, that's supposed to be 0. That's going to allow us to solve for AY. Now note also, everything else is also obtainable by superposition. So if we want the displacement in the real system at B, the sideways movement, we can get it by the sum of what happens in the two individual systems. So we'll do that also here. So there's our compatibility equation. Let's go find out this unknown reaction. A is 0. We found out that the primary displacement was downwards 2160 kip-foot cubed. We found that due to a unit load out there, we had an upwards 2304 kip-foot cubed over EI per kip of unit load. And the scale it up by AY, solve then for AY. Notice the units kip-feet cubed over kip-feet cubed. The EIs go away, and we're left with a kip because in reality that flexibility coefficient was a displacement per unit load. And that means that our reaction, when we work that out, is 0.9375 out here at AY. Right? Then we just apply basic equilibrium, and that's what you see worked out here. We get the reaction horizontally at C just being the 10 kip. We get the vertical being a hold down force. Sort of makes sense here. This thing is trying to overturn this, trying to push down at A and pull out at C, and then we get the leftover moment that isn't captured by the 0.9375 times 12 feet is going to be then the 48.75 acting clockwise on the member end. From that then we can go and get shear moment diagrams and the deflected shape. Okay, so the vertical reaction out here at A was, of course, 0.9375. There's no applied force out here, so that's going to be constant all the way through. Okay, and so then if we look at the column this way, then left to right we'll have a shear that looks like this. This is not drawn to scale, but we'll have 10 and 10 kips there associated with that load. Right now the moment diagram is going to just be this linearly increasing moment diagram, right? Starts off at 0. We have a positive slope of 0.9375. 0.9375 times 12 is 11.25 right there. Okay, and we turn the corner and we're going to have 11.25 here. The shear is 0, so that is constant down to the mid height, still at 11.25, and then we get this decrease going on here. So from the perspective of our positive being up there, right, little local coordinate system for that member being established right there, this would be the effect of a negative, and that's going to take us to then dropping down by 6 feet times 10 kips, or negative 60 kip foot. That's where we get the 43.75, and by this sign convention then this would end up being a negative, not 43, but 48.75 to get us to there, and that gives us our moment diagram from which we can then draw our deflected shape. Right, now we know now the curvatures, but gee, where does this thing end up going? How much sway do we end up? We know this end doesn't go down. It's on a roller that can move left and right, but it can't go up and down. The joint starts off at 90 degrees. It can translate, it can rotate, but it cannot go up and down. It can translate left and right, but not up and down. So we know we have some curvature here that's going to take us that direction. We know we have curvature there that'll take us that direction, and curvature there that will take us in that direction. But we don't know the left-right. We assume that it's going to move to the left. That would make a lot of sense, but we can calculate that. And that comes back from, again, a superposition principle here, that whatever we had happen at B can be thought of as the superposition of then whatever happened at B in the x direction in the primary plus whatever happened due to the unit load at A, unit load at A but causing a displacement at B, times the actual value of that reaction. And if we take to the left positive, then what we found out was, looking for all my sheets here, we found out delta BOX was 1,800 kip feet to the left. Over EI. And then what we found out for the unit load was that we had 864 kip foot cube acting to the right. That's per unit load. So minus 864 kip foot cubed over EI per kip of unit load. Our actual reaction was 0.9375 kips. So kip over kip goes away, and that's going to rescale that value. It is going to turn out to be positive, like we had, meaning to the left in this case. And we get a net of 990 kip foot cubed over EI. That positive is meaning in this case that we're acting to the left, as we had expected that it would. Right? So let's see how this all fits in then. We're going to move B to the left. There's your delta B. So that gives, and we got that numerical value. We want to get the elastic deflected shape in here. Now this is going to bend to the left until we get to the inflection point. And gee, where's that inflection point at? Well, that's going to be, this whole change is 60, 48.75 divided by 60 times 6 feet. That inflection point is at 4.875 feet. Okay, so as I think about how this is all going to play out, I'll go up about 4.875 feet. And there's our deflected shape. Now the curvature is going to change, and here's what I'm going to tell you to make sure you don't do. Don't swing this thing so that we actually end up with a net of a clockwise rotation up at the top. We can't have that. Why is that? Well, I'll show you in just a little bit. Alright, now it looks to me like I got a little too eager with my delta B symbol here, because look what's going to really happen to get this reverse curvature in there. That's going to have swung way much further over to the left than I've got showing. Okay, and I have to have a net rotation that's counterclockwise. Why? Because of the curvature that we have up here. That's why. So let me try to be a little bit more careful here about getting this It's not really to scales, but it is qualitatively to scale. And I got to have whatever the rotation is up here. Let's get that kind of reflected over. There's your theta b, and so I want to get that to be about also the same. That creates the construction line or the tangent by which then I can come along and more reasonably try to get that rigid joint and the curvature in. And there's your roller support out here, and there's your little right angle that's right there. Note again, the only way I could get that positive curvature in for that beam was if I allowed that joint to rotate in a counterclockwise fashion. I didn't want to exaggerate and string this really far back because I'd never get positive curvature to get me back down to here. Okay, so that gives you then the shear diagram, the moment diagram, a consistent qualified reflected shape, and an estimate of the sway.